Okay, I'll better stay here because sometimes I'll draw pictures. There are a lot of pictures in my talk, but nevertheless, some extra will be also helpful. So it's a joint talk with my colleague Pavel Sherbakov. And you see, the subject of my talk is not very traditional for optimization community. So I need some introduction, and it will be, first I'll formulate the problem mathematically, then I'll explain why it is of interest, and I'll show that there are numerous applications where such problems arise, and then I'll briefly say what is known about this type of problems, and then I'll provide some new results. Okay. So we have, actually, let's deal with finite dimensional problem, Rn. Then we have quadratic functions. We have quadratic functions. Actually, they are, in general, they are non-homogeneous. They include linear terms as well as quadratic terms. And the problem is very simple. We take quadratic transformation with components given by with this function. So it's transformation from Rn to Rm. And the equation, there are two versions. One is when we take the image, what is of interest, the image of the entire space, and in second case it's the image of a ball, for simplicity a unit ball. So remember that we denote E the image of entire space, and F the image of the unit ball. So the question is this convex set or not? Well, it's not that obvious, of course, and I always have in mind that we never assume that these matrices are positive definite or semi-definite. No, they are not. Okay. So where such problems arise? Of course, first of all, it's optimization. If we deal with general quadratic optimization problem, that's minimization of quadratic functions subject to quadratic constraints, then it's exactly a problem of this sort. And when such quadratic, so you see that we deal with equality constraints for quadratic functions as well as inequality constraints. And where it's very common in discrete optimization, when assumption that a variable is Boolean is equivalent that it's quadratic. There is a quadratic constraint. More interesting, for such problems, convex relaxation technique is well developed. So instead of such problems, we can deal, and I'll show what is it, some convex optimization problem. And the question when if the image which we deal with is convex, then convex relaxation is tight. And Okay, there are some application in control theory. I will not mention about it. It's so-called real mu problem, and also so-called S theorem in control theory, and so on. But what was a surprise for me, that there is a lot of applications in physics. And the initial push for this problem was our contact with physics from Skolkovo Tech. One of the problems was they deal with power systems. And surprisingly, they came to us and asked about similar convexity results. Why quadratic functions? Because power is a quadratic function of currency and voltage. So actually, the constraint and objective functions they deal with are quadratic. And they say many problems which relate to power nets, power grids, and so on, they relate to convexity or quadratic transformation. And another surprise for me was that the same problem arises in quantum theory, that say, I don't understand anything. I'm not a physicist, so I'm unable to say anything about quantum systems and so on. But there are dozens of recent papers in physics about, say, distinguishability of quantum systems, and they say that from mathematical point of view, it's equivalent to convexity or non-convexity of some quadratic transformations. Okay, so let's discuss this in general. First of all, well, quadratic, definitely the problems which I wrote, they were non-convex in general. But nevertheless, sometimes such problems behave as if they are convex. And the trivial example, it is everybody deals with it in linear algebra. When we minimize quadratic form on a unit sphere, the solution is known, independent, but it's non-convex problem because sphere is a non-convex set, and our quadratic form is not assumed to be convex. Nevertheless, the solution can be taken in explicit form immediately. It is the eigenvector which corresponds to the minimal eigenvalue of our matrix A. Okay. Then, this effect that sometimes quadratic terms lead to convexity, not in explicit form, but in some hidden form, it was understood long ago. And for instance, look at the titles of the papers like this. They write hidden convexity, or permanently going back and forth between a quadratic world and convex world. There are some links between quadratic and convex world. Okay, so what can be said about this? Is just two examples for you to demonstrate that in very simple cases. So it is the n equals 2 and m equals 2. It's a two-dimensional image of a circle. So, well, in this case it's convex, in this case it's non-convex, and well, what red, so blue points are just points inside inside the circle, and their images. Red points are points which are lie on the circumference of our circle, and their images. Well, and green is Pareto set. It doesn't matter now what is Pareto set and so on. But so you see, even in the trivial case, sometimes we deal with convexity and sometimes not. So what is known about this stuff? That, well, most results relate to low-dimensional cases. For instance, when the image is two-dimensional space, then image of the entire space or image of a ball, they are convex. It's non-trivial results. It's famous Dines and Brickman theorems. Well, they are a little bit extended. Sometimes the dimension of image is not important, but it's trivial case when all matrices commute. Then the image is convex. But of course, the situation of interest is when they don't commute. They cannot be transformed to diagonal form simultaneously. And well, another result is about convexity of image of a small ball. I formulated the problem as an image of a unit ball, but well, let's deal with the image of a ball of radius epsilon, and then it can be proved then for epsilon small enough, the image of a ball is convex. Well, actually, it can be easily understood why it is the case, because roughly speaking, for small epsilon, the main part of our transformation is linear. Quadratic term is just some small addition to linear map. And of course, linear map of a ball is an ellipsoid, so it's convex. And some small perturbation, ellipsoid cannot lose convexity after small perturbations. Okay, so these are mainly the known results when we can guarantee convexity of the image. Now about well, if our set is non-convex, then we can easily describe its convex hull. It's well, it's the idea of quadratic of convex relaxation. Actually, for quadratic functions, it was the idea goes back to Naum Shor as early as in 1986, And then it was developed by Yuri and many others. And well, there are many surveys on this stuff. And for instance, here is the description of this convex hole. So now instead of vectors, we deal with quadratic matrices, and we take a linear image. Here is this linear image, and this the same matrices A as in before, and these are scalar products of matrices, and so the convex hull of our image is a linear image of this set of non-negative definite matrices with bounded trace. Okay, it is the image of well, it is the case of homogeneous functions, homogeneous forms, and for non-homogeneous forms, but well, it's for the image of entire space E. Here is the description of convex hull. And actually, the idea of the proof is very simple. Well, of course, it's very well known that we can write our quadratic function as a scalar product. So our set actually is can be in matrix form. It can be written as follows, and if we get rid of this additional assumption that rank of our matrix is 1, then we immediately arrive to this convex hulls. Okay, these relaxations. Okay. So general question is, well, as I said, when our images coincide with the convex hulls or not. There are some results relating to how close, if they are different, how close they are. For instance, well, but maybe I'll skip it. But here is the example that, well, very simple example. Quadratic functions are written here. You see, they are as simple as possible. And the dimension is 3 and 3. And here is how the image looks like. Here, the green are the boundaries of some non-convex parts, so there are some inner parts there. So it's non-convex set. It's actually the sections are like this. These are these green parts, and there are points inside. Okay. Now, what can be said? So the question is, well, traditionally, the problem was, well, what are the classes of problems where can we guarantee convexity or non-convexity? Our point of view is slightly different. Given quadratic functions, so A, I, B, I are given, how to check, how to recognize if the images are convex or not? And so we try to get some certificates of convexity, non-convexity. Some of them are very simple. For instance, in this case, for homogeneous functions. If we cannot solve the LMI, if we can't solve LMI with respect to CI, and we can also find any vector which does not belong to our image, then definitely this image is non-convex. So why is it? Because if our image is convex, then it is either it is in some half space or it is the entire space. If it's in half space, we can separate it from zero, but this LMI is unsolvable. It means that it doesn't lie in any half space. And also it doesn't coincide with entire space because there is some vector which doesn't belong. So it's very simple. Actually, sometimes it works because, for instance, assume that all matrices have trace 0. And then linear combination of matrices has also trace 0. So it has positive and negative eigenvalues, and it can be semi-definite. Okay. Also, the convexity certificate also is very simple. It's again for homogeneous case. Assume that assume that for some C, no, not for some C, for all C, the linear combination of matrices has simple minimal eigenvalue. So it's not of multiplicity 2, 3, and so on, but it's always simple. Then our image is convex. It's very simple because, well, how it can be checked is just, if we minimize linear function on our image and it is the same that we minimize linear function on our convex hull, and if the solution is of rank 1, then we are done. Convex hull coincides with our set, and if and it's exactly the case here. Okay, so well, it's very simple, but unfortunately you can't imagine such matrices that their linear combination always has simple least eigenvalue. It's impossible, but nevertheless it works sometimes. And for instance, assume that it's positive matrices, positive in the sense that the entries of these matrices are positive. Then, due to Perron-Frobenius theorem, such matrices have simple largest eigenvalue, and well, here we deal with if we take C which are non-negative themselves, then the linear combination of matrices is again positive, and it has simple largest eigenvalue. So we are in the framework of the previous theorem, but not for all C, but just for a non-negative C. It means just that one part of our set is boundary of convex set. Okay, and another example is so-called Z matrices. When non-diagonal terms of matrices have some sign, they are non-positive, say, then we can theorem like that. Okay. Also, we have some results on local convexity. It means typical result is as follows. It's again for homogeneous case. So if we, for some C, we have this linear combination of matrices having simple least eigenvalue, then we can guarantee that for all other C close enough to this fixed one, we have the same situation. So we have some local convexity of our set. What is more interesting? It's non-convexity certificates. And here is the typical case. Okay, so it's again for homogeneous case. So we have quadratic forms, m quadratic forms of n variables, and assume that we found some C such that linear combination of our matrices have the least eigenvalue of multiplicity 2. Then also we assume some technical assumptions like this hold on. Then our set is non-convex. It's actually, what does it mean and how it can be proved? So what we are doing, we minimize linear function. We minimize linear function on our set F. It's equivalent to minimization of quadratic form with this matrix A on a sphere. Okay, if the minimum is if the eigenvalue is of multiplicity 2, there are two eigenvectors, orthogonal eigenvectors, which correspond to this minimal eigenvalue. So roughly speaking, the minimum is achieved in 2 points, and it's more difficult to prove that actually the minimum is achieved on two-dimensional ellipse on our set, but without interior points of this ellipse. So definitely this intersection is non-convex. And these assumptions, which I said, it's just to guarantee that our ellipse is not degenerate, that's indeed ellipse and not a straight line. Okay. And here is a very simple example. The dimensions are 3, n and m. You see these matrices. And this is the image. So it is exactly the case. So here are C, which we take. the matrix which arises, it is a matrix, a diagonal matrix with, so its eigenvalues, two eigenvalues are equal, and and the third one is not. And then we guarantee that the intersection of our supporting function of with our image is an ellipse, and it's exactly the case here. So it's such ice cream cone with non-convex head on it. So it's non-convex set. Okay. So now the question is, well, the theorem was, well, if we have such C that linear combination of matrices have the least eigenvalue of multiplicity 2, but how to find such linear combination? How to find such C? It can be done numerically, and well, there are several techniques. Well, actually it's solving some LMIs, and also another approach is, well, let me show here. So if we have again something like this, it's when it's non-convex, but we don't know, we are interested in C like that, which has two points of intersection or with two-dimensional image, but we don't have it. So we have one, then it's some C. We take eigenvalues, two least eigenvalues. They are not equal, but we take two eigenvectors corresponding, and roughly speaking, it is this point, and then we can easily geometrically construct this point, which is very close to our set, our convex hole, but it's outside. And by solving some LMI, we can find this flat part of the boundary, and it is exactly, it provides C, which is of interest for us. So I don't go into computational details, it can be done. Okay. And actually, just one result for non-homogeneous case. How we can guarantee non-convexity for non-homogeneous functions? The previous result was for homogeneous case. And so the critical situation, again, if we have some C such that the linear combination of matrices has zero, it's non-negative definite, and it has simple zero eigenvalue, and for corresponding vector, the scalar product of E, of this vector E and our vector B is 0. They are orthogonal. Then we again can guarantee non-convexity. And now the result is that, well, we have some intersection of supporting hyperplane with our image, which is a 2D parabola. And again, it's without points inside, so it's non-convex. Well, let me explain what is it. So it's a 3D image of 3D space with non-homogeneous quadratic functions. So these level sets are actually images of balls of radius of enlarging radiuses in our initial space. And what is important that well, actually, all the points inside this set, it looks like convex, but what happens here, you see this green part, it is some supporting hyperplane which touches our image, and it's exactly a parabola, as I said. Well, it's just a part of parabola here, but this is some non-convex part of our image. So in this case, we it's a certificate. This certificate of non-convexity works. Okay, what else? Now one can say, well, why do we need some analytical results on convexity and non-convexity? Well, let's just take sample points in our, if it's an image of a ball, let's sample points randomly in this ball and then take their image. So we expect that this pointwise image will be close to the true image. That's not. That's wrong. In large dimensions, say what is shown here, it's well, we take 100,000 sample points, and the dimension is just 25 n, and it's two-dimensional image, actually linear image of 25-dimensional ball. Points are uniformly in this ball, and you see their images are very bad approximation for the true image, which is a circle in this case. And there are, of course, it can be supported by formulas that just these approximations are too bad. And so such brute force method, just sample points, take their images, and this will be a good approximation for your image. That's wrong in large dimensions. It absolutely doesn't work. Well, maybe I'll skip this stuff. Well, this is again some examples how unexpectedly look these quadratic images. It is just a two-dimensional image of three-dimensional ball. And you see it's very strongly non-convex, and so on. So let me say a few words about our future plans. So first of all, I just explained situation with this image. When we can guarantee its convexity or non-convexity and so on. But if our original problem was optimization problem, then it's of interest to go back from these images to optimization. And it's interesting that, for instance, if we know that if we meet some non-convexity in the form of 2D ellipse in this image, and what is our optimization problem? It's when we have some constraints for our quadratic function. That is if we have some constraints, it's a section of our set of our image. And then we see that if our section of our image intersects with, say, with 2D ellipse, then definitely our optimization problem is non-convex, and so on. So we can translate this result to optimization stuff. Now, another question is, but what is typical for quadratic transformation? What is the, in some cases they are convex, in some they are not. So what is the typical picture, how it depends on the dimensions m and n? Assume we generate matrices and vectors randomly. So what can we say about probability of convexity and non-convexity? It's interesting, and some results can be, first we can just check numerically, but there are also some analytical approaches to this stuff, and it's of interest. Okay, so most of my figures were low dimensional. It's natural. I can just show you 2D or 3D images, but of course in physics, as I mentioned, it's power systems, and power systems, these are, say, something like electricity network of Russia or something like this, where dimensions are large and even huge. So how it works for large dimensional problems, how numerically can we deal with large dimensional problems, and again, how to apply to real life applications. Well, maybe that's all. Thank you.
Questions? Okay, so you showed us like functions like polynomials or quadratic functions.
No, they are not polynomials.
But
I don't say anything about polynomials.
No,
These quadratic terms, and it's very important that it's just quadratic terms, nothing more.
Yeah, anyway, can you use some multidimensional complex analysis, for example?
But what do you mean?
Well, because you know this problem, it looks very much like complex analysis problem. Like on the plane, there are many theorems on maximums of complex functions, and about the boundaries of there are different theorems which can connect, because one of the problems is that the boundary of your region, it goes into the interior of the image of the region.
Yeah, sometimes.
Yes,
sometimes.
And this is a problem, because when you say about a 25-dimensional ball, you're not obliged to generate everything. Maybe if you look on where goes the surface, the sphere, maybe you will find that it's already. So you need to generate
if the picture is the same, 100% the same. If all the points are on the boundary, the 2D image looks absolutely, there is no difference. Are they uniformly in a ball or uniformly on the sphere? 2D image looks similarly, absolutely. And it can be proved analytically.
Okay, thanks.
again, my question is related to it. So, in principle, it's interesting to find some results also for functions which are not very far from quadratic functions, like x and x. I met a problem where for one-dimensional case one can prove that the image is linear, very simple, but it is almost impossible to look at coordinates, check convexity of the image. Though I believe that some convexity is hidden in this problem. So how do you think that one can develop a good beyond quadratic functions?
Maybe, but the technique here strongly relies on quadraticity, because, for instance, this convex hull, which it is specifically quadratic technique. But you are right that, for instance, the result which I mentioned in the beginning about convexity of the image of a small ball, it doesn't. It is not only for quadratic functions. It's for any functions. Well, when we have some small nonlinear perturbation. So there are some results which work for non-quadratic functions as well.
Okay.